Because we are presumably masters of the energy transfer model, we should start to think about what energy is associated with charged particles. So to do that, I'm going to start with two particles, positive Q, and this other positive little q. And we know that there's some force between these two particles pushing this way and an equal force that way. We could define this force, the electric force, to be K, positive Q here, little q divided by the separation distance r squared. And let me define that r here. Distance between the particles. Okay, so I want to have you imagine that this little q is movable, this positive capital Q is fixed down, and we're going to take this little charge from infinity, where it's not feeling any force, and then bring it in closer, and we want to try and talk about the energy or the work that's necessary to move this particle into position. So in order to do that, in order to bring the charge closer, in order to bring Q closer, a force must be applied. Must be applied. And it's going to be in that direction, and it at least has to be larger than or equal to or greater than this electric charge. And notice that as we bring this charge closer, this force F will have to get larger, because the electric force is getting larger on the particle as it gets closer to this positive Q. So I want to think about the work that's done. The work done by this force F to bring the charge closer. So F here. And I know that work is force times the distance parallel, that is. I know that my force, I'm going to say that these two are going to be equal to each other, and I'm pulling this thing at a constant velocity, and that the distance will be from out here to this position here. And if I do a whole bunch of calculus, I can get this relationship and know that this is so hand-wavy because this course does not require calculus. Here's my force, my electric force, and my distance, I'm going to say, is the distance from the origin to positive Q, and I get the work done as KQ, little q, over R. Now, before we go any further, I want to try and make the analogy here to gravitational potential energy. So let's suppose that I have these bricks, and they're just hanging out here on some surface, and then you come along and you decide to push them up to a higher height. So now my bricks are, let's say, they're up here, and you move them up some distance h. The mass of the bricks is m, and so you should know pretty clearly that you added some energy into the system, and the bricks initially had 0 joules of energy. They weren't moving. We're defining this to be h equals 0. And then you came along and you did work. And you raised the bricks to a new height, meaning the bricks now have energy. The bricks now have mgh worth of energy. mgh of energy. Where did it come from? It came from you doing work, so the work you did is mgh. If it starts off with 0 joules of energy, now it has mgh of energy. You did that work. And so I want to make the connection here. Work is done to get these charges to be at their certain location, and that causes the system to gain potential energy. So here's my connection. When work is done on a system, the system can gain potential energy. And that potential energy for charges is electric potential energy. And if this is the work done to get these charges into place, well, this must also be the electric potential energy for charged particles, configuring charged particles. So let's look at this a little bit further. So my electric potential energy in the system, here I'm looking at positive Q and positive little q. Electric potential energy, and it's going to be so crucial that we make sure that we're saying that this is an energy. Alright, so this is the amount of work that was done to configure the charged particles into their position. The amount of work done to configure the charged particles into their position. And once stored, now the energy can be converted into other forms. Meaning if I bring these two particles into place and then I let them go, we would expect that they would move away from each other and get faster and faster and faster. So we would expect once this potential energy is stored, the energy can be converted. And we could look at this with a Lowell diagram or our mathematical expressions to other forms. Most notably, Ke. The particles will speed up. And so we're writing for a mathematical expression for electric potential energy between particles we have UE equals K QQ over R. I should also mention something about the actual charges and the signs associated with the charges. So let's look at finally positive Q and a negative charge here. Well, the charge will just the sign of the charge will be included in this expression. So we have positive Q, negative Q all over R. So this turns out to be KQ little q over R with this negative sign out in front. So as they get closer, there is a larger negative potential, which means our kinetic energy would be increasing. What if I have two negative charges here? We know that they're going to repel each other. And these two will get closer. Once again, we're just putting in the sign associated with the charge over R. So here we have a negative for this capital Q. We have a negative for little q. Both of those cancel out, and we get a positive value for our potential energy. And once we let these go, the potential energy in the system will decrease because this R gets larger, and that energy then turns into kinetic energy as these particles speed up in opposite directions. All right, that's electric potential energy. I will see you guys soon. Oh.